Okay, hello. I'm going to show you how to do this engineering question. Please watch till the end, or whatever. If you think you know it all, skip to the end, fine. Because I'm going to give you an alternative question to do. Okay, so we have this set up. Yeah, there's a V-shaped channel with water going through it, and we need to build a bridge across it. So it's going from here across to there. You can't really see it in that color here. So we're going to have to build like a bridge across there. That's what we need to do. Okay, so we got that. These are dimensions that I gave you. So we need to use a universal beam, and so obviously you're gonna have like 2 or 3 of these, and you're gonna lay the road across the top of it. Okay. So yeah. So this is the information I gave. So the way to do it, I'm not gonna take too long on this. So you have 4x plus 1 equals 7x minus 14. So then you just manipulate this. So what we're going to get is, whatever way you want to do it, you're going to get 1 plus 14 equals 7x minus 4x. I should be mathematically correct, so we should link the lines. That implies this. That implies 15 equals 3x. So that implies that x equals 5. So with that information, we just fill this in. So 4x, that's 4 times 5 plus 1. We know that this is 21, so obviously this should be the same. 35 minus 14 is 21. Cool. So now we have a triangle, and we have dimensions. So let me see if I put in this. So I'm going to do a shape polygon, right? So basically we have roughly there and down and okay, cool. So we have this kind of triangle here, don't we? So I'll just fill that in with red. Okay, so we have a triangle here, and we know that this height, or this length, is 21. We know that the vertical height is 4. So this is obviously not to scale. As I told you many times, do not go by what the shape looks like. Go by the information that you're given. If that says that's 2 million and this is 4, that's what you do, okay? So to scale like this would be way longer than 4. But don't worry about that when you see it. Just go with the numbers. So that's 21. We know the height is 4 because we're told it here. So we have a triangle. The hypotenuse is 21 and the height is 4. So I'm actually just going to do it up here. So Pythagoras' theorem is a squared plus b squared equals c squared. So we know that a is 4, or you could say b is 4, it doesn't matter. But we have one unknown. We have an equation with one unknown, and that's 21 squared. So what we're going to get is 21 squared is 441. So we're going to get b squared equals 21 squared minus 4 squared. So 21 squared minus 4 squared. So that means b squared equals, I really should connect these. That implies, so I'll just carry on over here. So I just want you to see that we are using Pythagoras' theorem here. So you know, it's it's all going back to Pythagoras' theorem, and it's not, you know, it's not some kind of magic. Yeah, that's it. So that implies b squared equals, 441 minus 16, so that equals 425. So that implies b, so we just do the square root of both sides, equals root 425. Now, if that was me, I'd leave it as the square root of 425, okay? Because that's an exact value. If you go into decimal, square root of 425 is going to be irrational, so it'll go on forever. So if it were me, I'd leave it as that, but I know maybe some of you don't want to do that, but that's fine. So we know that this height, this from here to here, is root 425. I'll just put it here. Square root 425. So we obviously have two of them, don't we? Because from here to here is also the square root of 425. So we've 2 times the square root of 425. So the length of the beam, we usually call that a span if it's going across open space. So let's just call it the span. It's the same as the length, okay? The span equals 2 times root 425. So I'm just going to do that. I'll just grab a calculator. Oops. Alright, so I have a calculator that I haven't used in a really long time. So we're going to do 2 times the square root of 425. So what I'm getting here is 41.23. Now, so that equals, I'm just going to go to 3 decimal places because that's millimeters, right? This is meters. You go to 3 decimal places, you go to millimeters. 41.23. So I'm getting 23105. So rounded to the nearest decimal, it's this. That's to the 3rd decimal place. But in engineering, you always round up, because if you round down, that means that you're making it less safe. So in engineering, you always round up for things that would make it less strong, and things that are more strong you round down. So that gives you safety. So in this case, if the span was longer, yeah, it would be worse. So you have to round up. So I'm going to go to 2. It won't make a big difference, but just make you aware that in engineering, things that could be negative, if you round up, then you round up, and things that could be like negative as in they could have a bad effect. So let's say you were doing what weight could this beam hold? So if you calculated it can hold 11.25 kilonewtons, well then you'd round up to like 11.3 or whatever, or 11.26. Anyway, you're probably bored with that. Anyway, this is meters. Anyway, so that's what we're going to go with. If you got 41.231, that's perfect, don't worry about it. Or 41.23, fine. But if you were to leave it perfectly, you just use 2 root 425. I think that's the same as 10 root 17 on your calculator, if you were to use the exact values. Anyway, we'll move on. I'm going to use 41.232. Okay, so we get the formulas here. So bending moment, so we know that L is equal to, we've done the hard part now. L is equal to 41.232. So to get the bending moment, we just say that equals, the load was 50, wasn't it? 50 kilonewtons. So it's 50 kilonewtons per meter. So we have 50 times 41.232. over 8, and that's squared. So I'm just going to 41.232 squared times 50 divided by 8. So this is quite large, to say the least. So it's 10, this is massive, 10,600. I'm going to round up to the nearest whole number because it's actually worse for us if we round up. So I'm just going to go like this. So in engineering, as I say, if it has a bad impact on your design, you round up because that makes it worse. And if it has a good impact on your design, you round down because that makes it worse. You're always looking for the worst case scenario because that makes it more safe. It might make sense to you now, but when you do the question, you'd see. The units are kilonewton meters. Just an explanation. So W is in, remember it was 50 kilonewton, capital N, meters. 8 has no units. L, is 50, is 50 kilonewtons per meter, right? And then the L is obviously, we're squaring it, so that's meters times meters, which is meters squared. So what happens is we're dividing by meters here, but here we have meters squared, so that will just make it take one of these meters away, so you're going to get kilonewton meters. Anyway, that's it. The next one, you'll see it down here again. I'll do it in a different color. So WPL is the plastic section modulus. Yeah, it's here. So that literally just substitution. They're scary numbers, but don't worry too much about it. 2, 0 to 4. So that's from here. Fy, so that's the stretching. They don't call it the stretching strength. They call it the tensile. You know, tension. When you put a string in tension, you stretch it. It's the tensile strength, but I just call it stretching so you'd understand. So it's 275,000. And we're going to divide that by gamma MO, which is the quality of the steel. Alright. You will get gamma M1 and gamma M2. They'll be like 1.1 or 1.2. It's a few years since I did this, but whatever. It's just 1, so it makes no difference. So that equals, let's try it. So 0.002024 times 275,123. So it's 556. So because this is our resistance, I'm going to round down. So you probably got, I'll put it exactly, it doesn't matter. 556.6, but you would round that down because that's, the bigger that is, the more helpful. You always put it the worst case. So you'd probably round it down to 556 exactly. But that's it. So I hope we can see that this beam is way too, I shouldn't say weak because it's actually a big beam, but yeah, it's not strong enough. Because on the top, this is the bending moment that it's the bending force. Think of it, it's not a force, it's a force by a distance. But it's the bending that the beam is actually getting from the weight is 10,626 kilonewton meters. But the bending that it can actually resist is only 556. So this is 20 times bigger than this, you know, or whatever, almost 20 times bigger than this, probably like 19. So actually you didn't have to do the rest of the question because the beam fails on bending. So it fails, right? Because, so you can say 10,626 is greater than 556.6. Yeah, therefore, you know, these little, therefore, beam fail. If the beam fails, so there's no point in checking it for deflection because it fails in bending. The beam fails, so you'd have to tell the architect, no, it's not. It's not big enough. And I'm going to reveal some information at the end too. Anyway, so let's check it for deflection anyway. This is actually going to be worse, believe it or not. So deflection is 5WL to the 4 over 384 EI. So that equals 5 times W was 50 kilonewton, kilonewtons per meter. L was 41 point, what do we go with, 232 to the power of 4 over, so you can see it's just substitution, 384 times E is 210 million. Usually these units would, like E would usually be in newtons per millimeter squared, and this would be also newtons per meter squared. This would be in centimeters cubed. This would be in centimeters to the 4. But I just put them in friendlier units for you because you've never done this before, obviously. Well, probably, I'm guessing you've not done it before. So I put them in like friendlier unit, but it's virtually the same. Not a huge difference. 99% the same. And I, wow, 0.000041232. 0.000041232. So you do that out, and let's do it. So it's 5 times 50 times 41.232 to the power of 4 divided by 384. Divided by 210, 123, 123. Wow. And then divided by 0.0041232. So I hope you can see it's very easy. If you left out a 0 here, you would say that the deflection is 10 times smaller than it actually is. So in engineering, you have to be very exact. If you left out one of these zeros, say you thought it was 2 zeros, you're going to say the deflection is smaller. So you're going to say, oh yeah, that's okay, the deflection is really small. But then when you go and build a bridge, you find that it's 10 times bigger because you left out a 0 by mistake. So it's these little tiny things. So the deflection that I am getting is a bit small. So I'm just going to double check one more time. 5 times 50 times 41.232 to the power of 4 divided by 384 divided by 210, 123, 123 divided by 0.1234132. Yeah, sorry, the deflection I'm getting is not small because so the answer, so this is sigma deflection. It's not small. It's 21 point. I did have to double check. I'm going to round up. So this is meters. Usually you'd expect something like this in centimeters. This is massive. This is gigantic. Imagine that this came down 21 meters. This beam was way, way, way too small. This is a definite fail. Okay, the allowable, this should have a subscript max here because it's the max deflection. Let's just do this. So that's what the actual deflection is. Imagine you had a bridge and it deflected 21 meters. Like, this is going to fail 100%. Length of beam. So let's go 41.232 over 300. So obviously it's going to fail. This is a total fail. 41.232 divided by 300. So you're allowed actually 0.137, I think it's 44, but anyway, whatever, meters. So you're allowed 13.7 centimeters. That's what you're allowed, but you actually have 21 meters. So you can write it wherever you want. You just go 21.732. We didn't have to check this because it failed in bending. Is way bigger than 0.13744. Yeah, therefore fail, it fails. Alright, so that was how you did it. So I asked you to watch till the end. So the thing is, when I made this question, I made 2 versions, and I gave you the wrong version. I'm sorry. Because this is so stupid, because this beam is massive. This length, there's no way this would happen in real. There's no way you're going to get a beam that spans 41 meters. So there's like there's a beam deflection calculator. If you put our values in, you go to Omni calculator. So our setup, you can go whatever setup you want. We've a simply supported beam, uniform load. Our span was 41.232. Uniform load was 50 kilonewtons per meter. Modulus of elasticity, I think it's 210, isn't it? 210, 1, 2, 3 million. Moment of inertia. Moment of inertia is another way to say second moment of area. What was our second moment of area? Second moment of area was 0.0041232. So let's see, I'll put that in. Hopefully they'll get the same answer as us. So I go 0.000411232. Yup. So they are getting, yeah, see that's millimeters. If you put it in meters, boom, 21.732 basically. What did we get? I think we got the same, didn't we? Yeah, 21.732. See, we got the same. And if you did it for bending moments, you get the same. So I was supposed to give you, that's why I think Hashem in year 9, boys. So this would not make sense. You're not going to have 41 meters across here. Hashem in year 9, boys, said to me today, like, he got a value of 41 meters for the beam. And I was like, no, it shouldn't be that. So the real question is here. So this should have been, if I can delete this should have been actually that's what it should have been. It should have been 4x minus 15, and this should have been 7x minus 30. That's what it should have been. So that's why I got confused today when he asked me. So what I want you to try, I'm going to upload this sheet, and what I want you to try is try this question with those values. So it should only take you about 15 minutes max, probably less. How long is this recording going for? I mean, I'm trying to write 23, it'll take you way less than that. Try this with those values, 4x minus 15 and 7x minus 30. And I hope we get different values. So sorry about that. I'll upload this and I'll upload the new one. Alright, thank you and adios.